Some of you had questions still about drawing resonance structures and using the curved arrows. So I thought I would just put together another video with a couple of extra problems here so that hopefully you get the hang of things. I just want to review the rules of curved arrows in resonance. You don't want to break single bonds in resonance. Never exceed an octet for second row elements. That means that any sp3 carbons also should not be getting extra electrons. Second row elements, including boron, carbon, nitrogen, oxygen, fluorine, will rarely, but sometimes they will have less than a full octet. So we may see things that are positively charged because they don't have a full octet. And the charges in resonance contributors should be balanced. That means that if you start with a neutral charge in your molecule, your resonance structure should have a neutral charge as well. So there's a couple of things you want to do when you're faced with drawing a resonance structure. You can ask yourself these questions, and we'll answer the questions as we go through this structure here. So the first one that I like to do is to ask if there are sp3 carbons. If you can spot the sp3 carbons, then we know that that is where we can't put any electrons. An sp3 carbon will have single bonds, and no charges. So it will not be positive or negative. So in this structure here, the first carbon is an sp3, as is the last one. So I do not want to draw any resonance structures where electrons get put into those carbons because they already have a full octet. Where can I put my electrons? So the places that you can put electrons are sp2 carbons, or you can put them onto heteroatoms. You can put them into carbons that are positively charged. So a positively charged carbon, this is missing a pair of electrons. That's why it's positively charged. So the missing pair of electrons, you can think of it as an empty orbital. That one is willing to accept a pair of electrons. And that we have no heteroatoms in this molecule, so we're only dealing with carbons and sp2 carbons here. What is then the overall charge of this molecule? Our charge here is positive. Now when I go to draw my arrows, I can only move electrons where there's sp2 carbons and where there's positive or negative charge. And here I'm only dealing with a positive charge. So I can take these electrons from the pi bond here and push them into this bond. And when I do that, my electron pair has moved to here, to between this, and because I took electrons out of this carbon right here, my positive charge has shifted to this carbon. That is the only resonance structure that I can draw. There are no other resonance structures because I can't push electrons into the sp3 carbons. So those two carbons on the end are forbidden. Okay, the next example here, I'm going to look for sp3 carbons. And the structure is different than the one on the last slide. I do have still sp3 carbons on either end. These are the single bond carbons. There's no charges here. So I only have those. So I'm going to cross that out so I'm not tempted to put electrons into those carbons. My electrons here, they can go into sp2 carbons to form a double bond, or they can go onto a carbon. And right now my net overall charge is negative. And you can go back and check on the last one. Our net charge is positive there. So what I can do is take the negative charge. These electrons can go to form a double bond here. So I'm taking those electrons to form a double bond. That would create 5 carbons at 5 bonds to this carbon right here. And so I can't move these electrons to form a new bond. I'm going to cross that out, or this would be pouring electrons into an sp3 carbon. So we don't want to do that. Instead, I'm going to put the electrons onto the carbon. So I'm allowed to put them on the carbon, but I can't put them into this bond without breaking rules there. So I'm going to draw the double bond right there. And then my electrons moved onto this carbon right there. My overall charge here is negative. There's no heteroatoms where I can put the electrons. So all I've done is moved it from this electron lone pair was on this carbon. It's now gone in to form the double bond, and that pi electron from the double bond is on the carbon. So that is one more resonance structure there. In this next example here, are there sp3 carbons? So I'm going to look for sp3 carbons, which are indicated by single bond carbons that do not show a charge. So I have one here, that's an sp3. This is also sp3. So I have two sp3 carbons where I cannot put any electrons. And the only places that we can move electrons are onto our sp2 carbons, which we have 3 of here. So there's 3 sp2 carbons. However, if I try to move these electrons from this bond right here, there's nowhere for these electrons to go. We can't jump carbons to put electrons over here. So this is not allowed. The electrons can only move one bond at a time. So there are no resonance structures possible for this structure. That sp3 carbon in the middle breaks up the conjugation, so we can't move the electrons any further than where they are at. So we look at this example. Where are our sp3 carbons, if we have any? There's one on the end here. That is the only one. That means that our electrons can go anywhere along these 5 carbons. Anywhere along those 5 carbons, including that sp2 carbon on the end with the positive charge. So I can move these electrons from between 3 to 4 to form a bond between 3 and 5. And by doing that, I've taken electrons out of carbon 3, so that is now positive. I can move the electrons from 1 to 2 into the 2 to 3. And that makes that carbon that I've labeled 1 positive. So those are my resonance structures there. There's no heteroatoms that I need to worry about. My overall charge in each of these structures is positive 1. And again, I've not put any electrons into that sp3 carbon because that's not allowed. In this next one here, we have sp3 carbons here, here, and here. So you don't want to be tempted to draw any electron resonance structures where electrons are being put onto those carbons. I can put the electrons into sp2 carbons, which is where the negative charge is right now. The one where the carbonyl is, the C double bond O, is sp2. And I can also put electrons on that oxygen. So the electrons from the negative charge can form a bond right there, and that will force electrons to go up there. My carbon skeleton stays the same. I form a new double bond there, and the negative charge is now on the oxygen. So that is one resonance structure. A less popular one would be to put the electron lone pair back onto that carbon. That negative charge is still there, but now the positive charge is on the carbon here, and then I have a negative right next to it. So that would be a rare, less likely resonance structure. So the overall charge, -1, -1, -1. In this example, sp3 carbons. I have one here, I have one here, here, here. And I have one out here. So I don't want to put any electrons there. So my electrons can go where there's lone pairs, like the heteroatoms, or sp2 carbons. So these are sp2 over here, but they're too far away to draw resonance structures from where the positive charge is. So the resonance structure that I can draw here is that I can take the lone pair electrons from nitrogen, form a double bond between that nitrogen and that carbon, and those will go on to the oxygen. And there's a new double bond here. The positive charge is now on the nitrogen because it's making 4 bonds. And that is one of the resonance structures that you can draw there. In this structure here, there are no sp3 carbons, so we can push the electrons into any of the sp2 carbons, which is all of them in the ring, and also on the oxygen. Oxygen cannot take any more electrons than it has right now, but it's okay taking the ones that it does have. So I can take the electrons from the oxygen. I can take the electrons from the oxygen and form this double bond. That's going to form 5 bonds to that carbon, so I'm going to put these onto this carbon right there. So I form a double bond there, and the negative charge goes on to that carbon. And I can go around the ring with that. So these electrons can form a double bond, and these electrons that are in this double bond right here can go on to that carbon. And then I can push these into this bond. That goes on to that carbon. These can go into here, and those electrons will go back onto the oxygen. So when you're dealing with more electron lone pairs and places where you can put the electrons, you're going to have a lot more possible structures. So that one has several resonance structures. In this example here, we have 0 sp3 carbons, so all of the electrons can go around the ring just like it did in the last example. So I can take these electrons, put them in to form a double bond there, and then these can go onto that carbon. And these can further go in to form a double bond. These go on to that carbon. And that negative can just go around the ring. We put our electrons in sp2 carbons. There's no heteroatoms here. Our overall charge has stayed at -1. In this example here, our sp3 carbons are here and here. So don't be tempted to put electrons into there. The first place I can move it is take these pi bonds right here and put it in to form a double bond there. So that positive charge means that it's an empty orbital and I can put electrons into there. So my double bond is now here and the positive charge is there. I can take the electrons out of this double bond and put them into there. And there's a positive charge there. And again, don't be tempted to put electrons into those two sp3 carbons that we crossed out. These are the two resonance structures that we have here. All right, in this example, the sp3 carbons are this one right here on the end, so there's just one. My electrons can go on sp2 carbons, which is the carbon here. So that one is sp2. And that has an extra pair of electrons, which is why it's negative. And we can also put electrons in sp orbitals. Or sp carbons, pi orbitals. So the electrons here can go from this carbon that I indicated as sp2. Those electrons can go into form a pi bond there. And then that would force too many bonds to carbon. So these electrons can go on to the carbon. So I would have a double bond here, and that carbon on the end is going to take a negative charge. So this would be another resonance structure for that one. In this example here, the sp3 carbon is on the end, so no electrons there. I can do actually the same arrows here. These negative charge electrons can go into form that double bond. Nitrogen is a heteroatom that can accept a lone pair. So we'll see a negative charge on the nitrogen and this double bond right there. I'm just putting a dot there so you can see where the carbon is. So nitrogen here would have two lone pairs, which is why it is negatively charged. Negative charge overall on both resonance structures. And that is an extended explanation for resonance structures. Hopefully you found that helpful.